If we allow the ring-to-ring flip, both chair conformations are possible. So a specific substituent is going to be partially equatorial and partially axial, depending on what chair conformation we're looking at. Now, this mixture isn't necessarily a good thing. The same substituent can vary in reactivity depending on whether it's in the equatorial or axial position. A large t-butyl group will allow us to lock the ring, and so only one chair conformation is energetically possible, and that's the one where the t-butyl group is in the equatorial position. Not only must the t-butyl group be entirely in the equatorial position, but the other substituents must be entirely in the axial position or entirely in the equatorial position if they have a specific cis or trans relationship. This will allow us to study the relationship between reactivity and the equatorial and axial positions with a substituent. Such substituents would include a bromo group, as we can see here. We're going to look at a 1,2 cis disubstitution pattern. Cis tells us that the two substituents are on the same side, either 2 up or 2 down. And we also know that one of the substituents will be equatorial and the other will be axial. Well, we know that the t-butyl group will be equatorial. Therefore, the bromo group must be axial, and we can see it here in the chair conformation. Moving from cis to trans, we're going to look at the 1,2 trans disubstitution pattern. Trans means the substituents are on the opposite sides to each other. So 1 up, 1 down. And where this is 1,2, it translates into equatorial, equatorial for both substituents. It's possible it would be axial and axial if it wasn't a t-butyl group. But we know a t-butyl group must be equatorial, therefore the bromo group must also be equatorial. And we can see it here in the chair conformation. Moving from 1,2 disubstitutions to 1,3 disubstitutions. And here is the 1,3 cis disubstitution. We know that the two substituents are both in the equatorial position. If the t-butyl group wasn't present, the axial-axial would also be possible. But we know a t-butyl group must be in equatorial position. Therefore, in this case, the bromo group also must be in the equatorial position. And here is the chair conformation just to double check that. Okay, what about the 1,3 trans disubstitution? Well, here, one substituent is up, the other is down, and one substituent is equatorial while the other is axial. And hopefully by now you know which substituent is going to be equatorial. That's right, it's the t-butyl group. Therefore, the bromo group must be axial. On from 1,3 disubstitution to 1,4 disubstitution. And here is the 1,4 cis disubstitution. Here, both substituents are up or both substituents are down. And one substituent is equatorial while the other substituent is axial. We know that the t-butyl group must be equatorial, so therefore the bromo group is axial. And again, here is the chair conformation. You can see that for yourselves. Okay, what about the 1,4 trans disubstitution? Well, now we're looking at 1 up, 1 down, and so we can also see that the two substituents are both equatorial. And again, they would be both axial if it weren't for the t-butyl group that's here. The t-butyl group must be equatorial. Therefore, the bromo group also must be equatorial. And we can see this in the chair conformation. So we can see a lot of variety here. We've got 1,2, 1,3, 1,4 substitutions. We've got cis, we've got trans. Look at every single example. every single example has the T-butyl group equatorial. Okay, T-butyl group simply never ever goes axial. But there are some subtler patterns here that I'd like to point out to you. When we change a number by 1, so we go from 1, 2 to 1, 3 disubstitution, or maybe we go from 1, 3 to 1, 4 disubstitution, what happens is we change from the substituents being equatorial axial to the substituents being equatorial equatorial and axial axial if they weren't T-butyl groups. Or vice versa, they may change from equatorial equatorial to equatorial axial. But one number change means, if you will, one letter change. Let's look at that. So here we have 1, 2 cis. It's equatorial axial. When we look at 1, 3 cis, so changed by one number, we go to equatorial equatorial, one letter change. When we go from 1, 3 with equatorial equatorial, one number change to 1, 4, we're now looking at equatorial axial. One number change, one letter change. Let's check that in the trans series as well. Okay, so here we have 1, 2 trans. It's equatorial equatorial. Let's go from 1, 2 trans equatorial equatorial to 1, 3. One number change, so it's going to be one letter change. So 1, 3 is going to be equatorial axial. Let's go from 1, 3 to 1, 4. We go from equatorial axial, one number change, so one letter change. We must have equatorial equatorial for the 1, 4, and that's true. So one number change, one letter change. But there's something else going on here as well. If you change from cis to trans, keep the numbers the same, just change cis to trans. One change in cis trans, one change in a letter. Let's look at 1, 2 cis, it's equatorial axial. When we look at the 1, 2 trans, cis to trans, one letter change. So it was equatorial axial for cis, trans is going to therefore be one letter change, so equatorial equatorial. So if you know what 1, 2 cis disubstitution pattern is, if you know those little patterns, you can anticipate all the other possibilities. So that helps out a little, I hope. Now, there are not only the cyclohexane rings that this can be true for. We can also see this where a nitrogen is part of the 6-membered ring. The lone pair of the nitrogen is going to be smaller than any other substituent. So any other substituent is going to prefer to be in the equatorial position. So normally the lone pair nitrogen prefers to be in the axial position where there can be no 1, 3 diaxial interactions.